This is a question about the mean value theorem, and like I said in class, it's a little hard to ask questions about this on exams because most of the questions in the chapter ask the student to perform a derivation. And I haven't talked much about doing derivations, and you probably haven't done many of them, so we have to fish around for other types of questions. So this is this is probably the easiest possible mean value theorem question. Verify that the function satisfies the hypotheses of the mean value theorem on the given interval, then find all numbers C that satisfy the conclusion of the mean value theorem. So what are the hypotheses? The hypotheses are that f is continuous and differentiable. So it has to be continuous on -1 to 1, and it is because it's a polynomial. And f has to be differentiable on -1 to 1, and it is because it's a polynomial. So polynomials are very nice functions. Alright, so that takes care of the first part, and now we just have to find number C that satisfies the conclusion of the mean value theorem. So what is the conclusion of the mean value theorem? So the mean value theorem, remember the picture is like this. You have 2 points, then you continuously and smoothly connect them, and then there has to be some input where the tangent line is parallel to the secant line that connects those 2 points. So what the mean value theorem says is that C exists where C is the special number, where f prime of C is equal to the slope of the secant line, which is f of b minus a, f of b minus f of a over b minus a. Okay, so this expression describes the slope of this line, and of course the derivative describes the slope of the tangent, so there must be some point where the slope of the tangent is the same as the slope of the secant line. And we're going to try to do this for this particular function, which I've graphed over here on the left. Here it is, and I've already plotted the secant line too. So it looks like this, and this isn't really necessary to do the problem. You won't have this on the exam, but it maybe will just help us figure out what's going on. So the first thing we should probably do is take the derivative. So the derivative is 6x plus 2. And alright, so this is talking about f of c, so let me kind of plug c in there. So what is f prime of c is going to be 6c plus 2. And what is supposed to be true is that 6c plus 2 is equal to this thing. And what is that? That is f of b, which is the right-hand point, minus f of a, which is the left-hand point, over the difference between the two, and that is 1 minus minus 1. So what does this number turn out to be? This number turns out to be, if you just figure it out, it must be 2. And let's double check. So if you plug 1 in, you get 3 plus 2 is 5 plus 5 is 10. Okay, so f of 1 is 10, and then you're taking away f of minus 1. So what happens when you plug in minus 1? You get 3 minus 2 is 1, plus 5 is 6. So the numerator there is going to be 4, and in the denominator you've got 2. So 2 over 4, and yes, okay, so the answer is 2. So we have to solve the equation 6c plus 2 equals 2, so that says 6c equals 0, and so that means that c is equal to 0. So what does that mean for our picture? It means that it must be that the tangent line here at 0 is parallel to this line. So let's put it in there and see that that's true. All right, so we're gonna so what is f prime of 0? F prime of 0 is going to be 2. Oh, that's a good sign. I mean, already we know it's correct for that reason. So f prime of 2 is equal to, or sorry, f prime of 0 is equal to 2. So if we use point slope form or the formula for L, which is always good to practice, you know, we need f of 0 plus f prime of 0 times x minus 0 is going to give us the tangent line there at 0. So what happens when you plug 0 into the original function? You get 5. So this is going to be 5 plus 2x, right? And green is a lovely color, so let's put it in here as 5 plus 2x. Bam! So you can see that it works, right? The mean value theorem says that there was such a point, and there it is. You can clearly see that it is. Whoa, did I forget to... Yeah, I forgot to copy down that problem correctly. Shoot. Man, I hate to make you wait while I do this, but I guess I need to look up the question that I forgot to write down. Sorry about that. Section of the book on mean value theorem, and we're supposed to verify that, let's see, I keep trying to write on the trackpad. So let's do this one, x cubed minus 15x plus c. Okay, we're supposed to, and I really hate to use c, so I'm going to use a different letter, d, equals 0, and in the interval, from -2 to 2. Okay. All right. So I think the questions of this form are really fun. I mean, you're going to show something doesn't exist. You're showing that the second root doesn't exist. So that's always interesting to prove something doesn't exist. So let's draw. No, we don't really need to draw any axes. So what's the argument going to be here? If we take the derivative of the function, it's going to be 3x squared minus 15. And so if this function did have 2 roots, then what would it look like? Oh, man, sorry. If it had 2 roots, let's say it had a root here, it had a root here. So it's it's one of these cubic functions, so it's going to sort of probably look like this. So there's several things that are possible. So it could go like that. I guess the point is supposed to be an application of Rolle's theorem between the two roots. So if there were 2 roots, then Rolle's theorem says that there has to be some point in between where the tangent line is horizontal, right? So that means there has to be some point C where f prime of C is equal to 0, and somehow that must be absurd. So let's see why. So let's set this thing equal to 0. So what could possibly make this true? We've got x squared is equal to 15 over 3 is equal to 5, and so this gives x equals plus or minus the square root of 5. And it must be that, remember, we have actual values here. So this is minus 2, and this is 2. And the square root of 5 is bigger in magnitude than 2, so the square root of, because 2 squared is 4. So the square root of 5 is going to be over here, and negative square root of 5 is going to be over here. And so what we've shown is that this thing is a critical number, but there are no critical numbers in the interval. So no crits. So because there are no critical numbers in the interval, there can't be a flat place on the graph. So do you see the argument? Let's summarize here, okay? So suppose by way of contradiction that there were 2 roots. Then by Rolle's theorem there is a critical point between the 2 roots. But just by algebra we showed that there is no critical point between the 2 roots. Therefore the original assumption that there were 2 roots is absurd, and there is at most 1 root, and the argument is complete. Yeah, that won't be on the exam. This last question says, if f of 1 equals 10 and f prime, this is my way of writing on the keyboard, greater than or equal to 2. So if the derivative is always greater than or equal to 2, and 1 is always less than or equal to x is less than or equal, oh, on this interval, that's true. How small can f of 4 possibly be? Let's draw a picture. And again, I say this all the time, but when I see a student try to answer a question without drawing a picture, it really it makes me pull my hair out. You can't answer these questions without drawing a picture. So we're looking at the interval from 1 to 4, and what do we know? We know that f of 1 is 10, let's just say that that's there. And we know that the derivative is always greater than or equal to 2. Okay, so we want to know how small can f of 4 possibly be? Well, just on, a hunch here, let's say that it's right there. Okay, let's say that's where f of 4 is. And look at the secant line that connects those two. It goes like this. All right. So now let's ask how small can the slope of this green line be? So by the mean value theorem, however, let's let m be the slope of this line. However small m is, there must be some point c where f prime of c is equal to m by the mean value theorem. Actually, they lazily leave out the statement, which is really necessary, that the mean value theorem applies to f, so we have to assume that it's continuous and differentiable. But there is going to be some point c where the tangent line is parallel to m, and in notation that means that f prime of c is equal to m. And so we have to throw this into the mix. So we know that f prime of c is always going to be at least 2, and so that means that m must be at least 2. And if m, that means that the smallest m could possibly be is 2, so that's going to give you your smallest value, right? So let's suppose now m actually is 2, then what is this point going to be? So every time we go over by 1, we're going to go up by 2 because the slope is 2. So that'll be, we go over by 1, that'll be 12, and this will be the point 2. And at 3, we're going to be 14, and at 4, we're going to go up to 16. So the smallest this can possibly be is 16. All right, so the answer is a number. You can get that right or wrong. So this could very well be on the exam. And that's it.